students. I am Professor Isha Medelata from LG Institute of Engineering and Technology. In our previous video, we had started with the module Superconductivity. We already have discussed the basics of superconductivity and few of the properties. So in today's session, I will be covering the remaining properties of superconductors. So shall we start? Starting with the fifth property of superconductor, that is critical magnetic field. What exactly is critical magnetic field? It is defined as the minimum magnetic field which defines the superconducting state. Now, what exactly happens when magnetic field is applied? What leads to the loss of superconductivity? This is when you apply a magnetic field to any superconductor, what happens? There's an external force which is acted on the electrons, which disturbs their coordinated motion, and that leads to the loss of superconductivity. Let's see what exactly superconductor behaves in response to a magnetic field. So suppose we have a battery connected to a superconductor. So on the right side you see a small superconductor. What will happen? You can just see in the diagram, the magnetic field lines are not passing through the superconductor, but then they are increasing the amount of magnetic field. At a certain value, you can see that the magnetic field lines pass through the superconductor. So this particular value which destroys the superconducting state is what is critical magnetic field. Moving on to what is the relation of this critical field? This is a function of temperature. Higher the temperature, higher will be the critical value. It is related by the formula Hc is equals to Hc naught 1 minus T by Tc square, wherein we have Hc as the critical field, we have Tc as the critical temperature, and the term Hc naught is known as the value of critical field at 0 Kelvin. Let's see how Hc and Tc are related with the help of a small graph. So we've plotted Hc on the y-axis and Tc on the x-axis. So 2 points on the x and y-axis we have superconducting phase. So only within this curve which is shown by green lines you can say that a superconductor behaves in superconducting state, else it will be in normal state. Moving on to the next property, that is critical current density. What do you mean by current density? It is defined as the current flowing per unit area. So let's see what critical density here means. It is the maximum current per unit area passing through a superconductor without destroying its superconducting state. If current density through a superconductor increases, again its superconducting state can be vanished, it is lost. Let's see how. So we have a small circuit. We just switch on the battery. The current starts flowing through the superconductor. You can see in the zoomed view that the ions are stable and electrons are moving easily. But if the current value increases, what happens if the current value increases? If the current value increases, the electrons start vibrating, and if they are colliding with the atoms, heat will be generated. So temperature is increased and your superconductivity is lost. There is a relation of this critical current density with the critical magnetic field, because any conductor through which current is flowing, magnetic field will be generated. So we have the relation IC is equals to 2 pi r Hc. This is based on the Ampere's circuital law. On the basis of this, we can define Jc, that is critical current density, as 2 Hc by r. So here IC is known as the critical current, Hc is known as the critical magnetic field, and Jc is known as the critical current density. Moving on to the next property, that is persistent current. What do you mean by the word persistent? Persistent means continuously flowing, which flows continuously without stopping, without decreasing. Superconductors are materials which exhibit this kind of persistent current. Let's see what persistent current means. So when current is made to flow through a superconductor, which is at a temperature equal to critical temperature or less than critical temperature, it is observed that current will flow without any significant loss. This steady flow of current through a superconductor is known as persistent current. Now, why current flows without significant loss? Because we know that superconductors do not have resistance. So the electrons can move easily, they will not collide with the atoms, and that is the reason there is no significant loss. Let's exactly see what persistent current is. So we have a simple battery at a normal temperature. It is passing through this normal metal. Now what we do is, we convert it into a superconductor by lowering the temperature. And if you remove the battery, you can still see that current is flowing in this ring. So even if the source is removed, because of zero resistance, the current keeps on flowing. This is what is persistent current. Moving on to our last property of superconductors, that is MEISSNER effect. The name is behind the physicist, which is behind the physicist who suggested or proposed this effect. Let's see what MEISSNER effect is. It says the complete expulsion of all magnetic field lines from a superconductor is called MEISSNER effect. What do you mean by the word expulsion? Expulsion means repulsion. Superconductors never allow magnetic field lines to pass through them. They will always repel the magnetic fields. This property of a superconductor is also known as the diamagnetic property. Let's see what MEISSNER effect is. This is YbCO, a very commonly used superconductor. So we're just placing superconductor. Then we have a small magnet. We are placing the magnet on the superconductor. You can see there is a contact between them. Now liquid nitrogen is poured. So this will lead to superconductivity in YbCO. And now you can see that the magnet is floating. It is no more in contact. Why is it floating? Because the superconductor opposed the magnet. So till it was not a superconductor, they both were in contact. And when it achieves superconductivity, it will repel the magnet, and that is the reason the magnet floats. MEISSNER effect says that if T is greater than Tc and H is greater than Hc, that means if a metal is in normal state, the magnetic field lines will pass through it. And we say that B, that is the flux within the metal, is not zero. But when you have T less than Tc and H less than Hc, that means if your metal is in superconducting state, what happens is the magnetic field lines are not allowed to pass. Instead, they just move away or move outward the superconductor. And we say that the flux density within the superconductor is zero. There is a very common equation we have studied in magnetism, which says that B is equal to mu 0 into M plus H, where B is known as the magnetic flux density, mu 0 is known as the magnetic permeability, M is the magnetization, and H is the applied field. This is a relation which relates all three parameters. For a superconductor, just in the previous part, we've seen that flux density is zero because the superconductor does not allow magnetic field lines to pass through it. So we say that B is equals to 0 for a superconductor. So our above equation becomes mu 0 M plus H is equals to 0. We know that mu 0 is the absolute permeability, which has a certain fixed value. So that value can never be 0. That leads to the equation M plus H is equals to 0, or we can say M is equals to minus H. What is M by H? Magnetism with respect to applied field is defined as susceptibility of a material. How easily a magnetic material allows magnetism through it. So if we get M is equals to minus H, we can say that M by H, the ratio chi M is equals to minus 1. Now this magnetic susceptibility is equal to minus 1 is for diamagnets, and hence we say that superconductors behave as diamagnetic materials. This was all about the properties of superconductors. Now there's a small topic which I am going to discuss, that is the three very important factors which define a superconducting state. There are three factors which govern a superconducting state. The first one is critical temperature. The second one is critical current density. And the third one is critical magnetic field. We've studied all the three in this video. What exactly is critical temperature? Now, why is it known as an important factor? Because if you increase the critical temperature, if you increase the temperature beyond this value, superconductivity is lost. Let us see the relation between these three. So on this graph, we have this as temperature axis, this as the current density axis, and this as a magnetic field. So if I join extreme points on this graph, I will get the surface which is called critical surface, and within this surface your superconductor behaves as a superconductor only, and outside this critical surface there is no superconductivity. It is known as normal phase. This was just a brief about properties of superconductors and what are the factors which define superconductivity. Hope today's topic were clear. I will be starting with types of superconductors in my coming video. Thank you.